Friends, welcome to the tutorial series on network analysis made simple. In this tutorial, we shall solve VTU CBCS scheme electrical circuit analysis paper of June-July 2018 module 2. Friends, I prefer to emphasize on basic circuit concepts rather than detailed mathematical steps. I am sure you have already well equipped with the required mathematical skills. I hope this tutorial ignites some of your thoughts. Let's go ahead. Friends, let us first answer question 1, in which we are required to state and prove the superposition theorem with an illustration. What do you mean by this? First, state the superposition theorem, then select a simple electric circuit and arrive at the proof. Friends, we know that the superposition theorem is applied to a multi-source network. It states that the response in any branch of a network is equal to the algebraic sum of the responses obtained by considering each source independently, during which time the other sources are forced to zero. To prove the superposition theorem, consider a simple circuit shown in figure. The network consists of two sources, a voltage source V1 and a current source I1. Let R2 be the load and IL be the load branch current. To prove the superposition theorem, we need to consider one source at a time and find the current in the load resistance R2. We know that when the voltage source is forced to zero, it has to be short circuited, and when the current source is forced to zero, it has to be open circuited. First, by considering only the voltage source as acting, the current source is forced to zero by open circuiting it. Let IL1 be the load current in R2 as shown. Friends, by doing so, we find that the circuit has reduced to a single loop network. So, by writing the Kirchhoff's loop equation, we get IL1 is equal to V1 divided by R1 plus R2. Next, by considering only current source as acting, the voltage source is forced to zero by short circuiting it as shown in figure. Let IL2 be the load current in R2. By doing so, we find that the two resistances R1 and R2 are in parallel across the current source of I1 amperes. So, by using parallel branch current division theorem, we get IL2 is equal to R1 divided by R1 plus R2 into I1. Now, the total current IL is equal to IL1 plus IL2. By substituting for IL1 and IL2, we get IL is equal to V1 plus I1 R1 divided by R1 plus R2. Friends, now we have to show that we get the same result by considering the original given circuit and finding the equation for the load current IL using any other suitable circuit solving technique. So, consider the original circuit as shown in figure. We find that the current source of I1 amperes is an ideal source. So, I2 minus I1 is equal to capital I1. And by writing the Kirchhoff's voltage equation for the outer loop, we get I2R2 plus I1R1 minus V1 is equal to 0. But from equation 3, we get I1 is equal to I2 minus capital I1. By substituting this value of I1 in equation 4 and solving, we get IL is equal to V1 plus I1 R1 divided by R1 plus R2. So, we find that the result is same. Thus, the superposition theorem is proved. Friends, next we shall solve question 2, in which we are required to obtain the Thevenin's equivalent circuit as seen by the load impedance for the network shown in figure. To find the Thevenin's equivalent circuit, we need to open the load branch and find VOC or VThevenin and ZThevenin. To find VOC, the circuit drawn by opening the load branch is shown in figure. We find that the circuit is transformed into a single closed loop network and current in 4 ohm is 0 as the branch is open. Let I be the current in the loop as shown. Hence, I is equal to 10 angle 0 divided by 5 plus J4 minus J4, and we get I is equal to 2 angle 0 amperes. But VOC is the voltage across minus J4 capacitance. Hence, VOC or VThevenin is equal to 2 angle 0 into minus J4. By solving, we get VThevenin is equal to 8 angle minus 90 volts. Friends, to find Thevenin's impedance, we need to force the voltage source 0 by short circuiting it as shown in figure. Observe the network. We find that 5 plus J4 ohm is in parallel with minus J4 ohm, and this parallel combination is in series with 4 ohm. So, Z Thevenin is equal to 4 plus 5 plus J4 into minus J4 divided by 5 plus J4 minus J4. By solving, we get Z Thevenin is equal to 7.2 minus J4 ohm. So, knowing V Thevenin and Z Thevenin, the Thevenin's equivalent circuit across the load branch is shown in figure. Hope it is clear to you. Friends, next we shall answer question 3. In this question, we are required to state Millman's theorem and apply it to find current flowing through RL in the network shown in figure. Friends, note that we are required to only state the Millman's theorem. Hence, we know that Millman's theorem is applied to find the current in the load branch which is connected across parallel connected sources. So, according to Millman's theorem, the equivalent voltage V equivalent across the load impedance can be determined by using V equivalent is equal to summation of VI YI divided by summation of Yi, where I goes from 1, 2 to 3 in this circuit. We also know that Z equivalent is equal to 1 upon summation of Yi. Using V equivalent and Z equivalent, the equivalent circuit across the load branch can be drawn as shown in figure. So, from the equivalent circuit, we find that IL is equal to V equivalent divided by Z equivalent plus RL. Friends, now let us apply the Millman's theorem for the given circuit. Consider the network shown in figure. To find V equivalent, we know that V equivalent is equal to summation of Vi Yi divided by summation of Yi. From the given network, we find V1 is equal to 20 angle 30 volts Z1 is equal to 10 ohm, so Y1 is equal to 0.1 mho. V2 is equal to 10 angle 0 volts, Z2 is equal to J10 ohm, so Y2 is equal to minus J 0.1 mho, and V3 is equal to 15 angle 45 volts, Z3 is equal to minus J10 ohm, so Y3 is equal to J 0.1 mho. Hence, summation of yi is equal to y1 plus y2 plus y3. By substituting the values, we get summation of yi is equal to 0.1 mho. But summation of Vi yi is equal to V1 y1 plus V2 y2 plus V3 y3. By substituting and solving, we get summation of Phi yi is equal to 2.987 angle minus 20.796. Note 15 angle 45 into 0.1 angle 90 is negative because the polarity of source 15 angle 45 is downwards compared to the other two sources. Friends, we know that summation of yi is equal to 0.1 mho and Z equivalent is equal to 10 ohm. But V equivalent is equal to summation of Vi yi divided by summation of yi. By substituting the values, we get V equivalent is equal to 29.87 angle minus 20.79 volts. Knowing V equivalent and Z equivalent, the equivalent circuit across the load branch drawn is shown in figure. From the equivalent circuit, IL is equal to V equivalent divided by Z equivalent plus RL. By substituting the values, we get IL is equal to 0.995 angle minus 20.79 amperes. Friends, it is so simple, isn't it? Friends, next we shall solve question 4. In this question, we are required to prove that the maximum power is transferred to the load in AC circuit when ZL is equal to ZS conjugate, where ZL is equal to RL plus JXL and ZS is equal to RS plus JXS. Since the given condition to be proved is ZL is equal to ZS conjugate, meaning both RL and XL in the load impedance branch are varying. So, the strategy will be, considering the simple AC circuit shown in figure, find the equation for IL and the equation for power absorbed in the load RL. Since both RL and XL part of the load are varying, first assume that only XL as varying and RL as constant. Then find dP by dXL and equate it to 0 and find the condition. Substitute this condition obtained in the equation of power and get the resulting equation for power. Next, use the equation of power obtained and find dP by dRL and equate it to 0 and obtain the condition. Then, use both the conditions and prove that ZL is equal to ZS conjugate. So, from the figure considered, we find that equation for the load current IL is equal to Vs divided by Rs plus RL plus J XS plus XL. From the equation for the current IL obtained, we know that mod of IL is equal to Vs into 1 divided by square root of Rs plus RL whole square plus XS plus XL whole square. Using the equation for mod IL, we know that P is equal to mod IL squared into RL. By substituting the values, we get the equation for power. First, assuming as only XL varying, RL being constant, and finding dP by dXL and equating dP by dXL is equal to 0, we get the condition XL is equal to minus XS. Friends, next, considering the equation for power and substituting XL is equal to minus XS and solving, we get P is equal to Vs squared into RL divided by Rs plus RL whole square. Now, assuming RL as varying and finding dP by dRL and equate it to 0, we get the condition RL is equal to Rs. We know that XL is equal to minus XS, and when both RL and XL are varying, ZL is equal to RS minus JXS. But ZS is equal to RS plus JXS. So, the condition for maximum power transferred across the load is ZL is equal to ZS conjugate. Friends, next we shall solve question 5. In this question, we are required to determine the Norton's equivalent circuit for the circuit shown in figure as seen by the terminals A and B. Observe the network. The network contains both dependent and independent sources. Hence, to find the Norton's resistance, we need to find both open circuit voltage VOC and the short circuit current ISC. To find the open circuit voltage VOC, the circuit drawn is shown in figure. Observe that all the resistances are represented in ohms and the source current is 0.7 amperes. Friends, in the network, we find two closed loops and let I1 and I2 be the assumed mesh currents. We also know that VOC is the voltage across 1500 ohm resistance. So, to find VOC, we need to find I2. Friends, because the network has an ideal current source of 0.7 amperes, by writing the constraint equation for that branch, we get I1 minus I2 is equal to 0.7. By writing the Kirchhoff's voltage equation for the outer loop, by tracing it in the anticlockwise direction, we get 1500 I2 plus 2Ix plus 500 I1 plus 2500 I2 is equal to 0. But Ix is equal to minus I1. Substituting for Ix, solving and rearranging, we get 498 I1 plus 4000 I2 is equal to 0. By solving the two simultaneous equations 1 and 2, we get I1 is equal to 0.6224 amperes and I2 is equal to minus 0.0775 amperes. But VOC is equal to I2 into 1500. By substituting the values and solving, we get VOC is equal to minus 116.25 volts. To find ISC or IN, we need to short circuit A and B as shown in figure. Observe the network. We find that 1500 ohm resistance is short circuited, hence it can be considered as open. The circuit redrawn is shown in figure. Now, the circuit has transformed into A two-loop network as shown in figure. Let I1 and I2 be the assumed mesh currents. By writing the constraint equation for the branch containing ideal current source of 0.7 amperes, we get I1 minus I2 is equal to 0.7. By writing the Kirchhoff's voltage equation for the outer loop, we get 2ix plus 500 I1 plus 2500 I2 is equal to 0. But Ix is equal to minus I1. By substituting for Ix and solving, we get 498 I1 plus 2500 I2 is equal to 0. By solving the two simultaneous equations 1 and 2, we get I1 is equal to 0.5837 amperes and I2 is equal to minus 0.11625 amperes. But I2 is equal to ISC is equal to minus 0.11625 amperes or IN is equal to minus 0.11625 amperes. Also, we know that Rn is equal to VOC upon ISC. By substituting the values and solving, we get Rn is equal to 1000 ohm. By knowing IN and Rn, the Norton's equivalent circuit as seen through the terminals A and B drawn is shown in figure. Hope you understood it. Friends, finally, we shall solve question 6. In this question, we are required to find the current in 5 ohm resistance and then verify the reciprocity theorem. Observe the network. We need to apply suitable circuit solving technique and find current I in 5 ohm resistance. This is the response and 100 angle 45 volts is the source. The network has 3 junction nodes and 3 independent loops. So, I prefer to solve for current I using node voltage method. Consider the network shown in figure in which V1 and V2 are assumed node voltages of node 1 and node 2 respectively. By writing the nodal equation for node 1, we get V1 minus 100 angle 45 divided by 10 plus V1 divided by J5 plus V1 minus V2 divided by 10 is equal to 0. By rearranging and solving, we get 0.2 minus J 0.2 V1 minus 0.1 V2 is equal to 10 angle 45. Similarly, by writing the nodal equation for node 2, we get V2 minus V1 divided by 10 plus V2 divided by minus J5 plus V2 divided by 5 is equal to 0. By rearranging and solving, we get minus 0.1 V1 plus 0.3 plus J 0.2 V2 is equal to 0. The equations 1 and 2 are represented in determinant form as shown. By solving for delta, we get delta is equal to 0.09 minus j 0.02. To find I or Ix, note that it is enough if we find V2. To find V2, let us use Cramer's rule. So friends, by replacing the second column by the last column and solving for V2, we get V2 is equal to 10.846 angle 57.528 volts. But I is equal to V2 divided by 5. By substituting and solving, we get I is equal to 2.169 angle 57.528 amperes, or Ix is equal to 2.169 angle 57.528 amperes. Friends, we also are required to verify the reciprocity theorem. For that, we need to interchange the position of source and the response. Consider the given network shown in figure. In the given network, the source of 100 angle 45 volts is to be introduced in the branch containing 5 ohm where the response is I amperes. Friends, after interchanging the positions of source and response, the circuit drawn is shown in figure. Let Iy be the response now as shown in figure. By writing the nodal equation for node 1, we get V1 by 10 plus V1 divided by J5 plus V1 minus V2 divided by 10 is equal to 0. By rearranging and solving, we get 0.2 minus J 0.2 V1 minus 0.1 V2 is equal to 0. Similarly, for node 2, we get V2 minus V1 by 10 plus V2 divided by minus J5 plus V2 plus 100 angle 45 divided by 5 is equal to 0. By rearranging and solving, we get minus 0.1 V1 plus 0.3 plus J 0.2 V2 is equal to minus 20 angle 45, or minus 0.1 V1 plus 0.3 plus J 0.2 V2 is equal to 20 angle minus 45. Friends, by writing the two simultaneous equations in the determinant form and solving for delta, we get delta is equal to 0.09 minus j 0.02. Note that we are required to find the response Iy, for which it is enough if we find V1. So, by solving for V1, we get V1 is equal to 21.639 angle minus 32.47 volts. But Iy is equal to V1 divided by 10. By substituting the values and solving, we get Iy is equal to 2.169 angle 57.528 amperes. We find that Ix is equal to Iy, hence the reciprocity theorem is proved. Very simple, isn't it? Friends, in this tutorial, we answered theory questions and solved numerical examples on network theorems. I am sure this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.